So we were talking about this pipe problem where the city wants to ensure that a vendor's pipe has at least 2,400 pounds per square inch strength to it. And so the city took 50 samples and tested them and came up with these results. So we set up a hypothesis where our alternate hypothesis was that the mean pipe strength for the vendor's pipes was greater than 2,400 psi, and the null hypothesis was that the pipes were essentially less than or equal to 2,400 psi. But to simplify what we're doing, we're just going to say the mean is equal to 2,400 as our null hypothesis. So what are we looking at? We're looking at a situation where we have a normal distribution, and we want to relate that to the standard normal distribution. So if we look at a 99% of the information in this normal distribution to the left of some z value, this is a critical z value then, and that value we know is equal to 2.58. It'll always be the same number. Whenever you have a standard normal curve, the area to the left of some value of z is 99%, that's always going to be equal to 2.58. That means you have 1% left over. So in this situation then, the way we relate these things to a normal curve is we use the z statistic, and we set ourselves up a test statistic here. Circle it. This z statistic. And we calculate this value based on the information from the sample set and from the population that goes into this. And one of two things can happen. We can end up with a calculated test value that is greater than this 2.58, or possibly a calculated test value that is less. So I'll just write z sub t is less than 2.58, or z sub t is greater than 2.58. Now, if our test statistic is less than 2.58, then what we decide is there's not enough evidence to reject the null hypothesis 8.0. On the other hand, if z ends up greater or inside this critical region, then we actually reject the null hypothesis. Now, when we reject the null hypothesis was that the population mean was essentially less than or equal to 2,400 or equal 2,400. If we reject that idea, then the other case must be true. So, if we reject the null hypothesis, then we could say with a level of significance equal to an alpha equals 0.01, we conclude that the vendor's pipe exceeds 2,400 pounds per square inch. Now, in essence, there's a possibility that we could be wrong. And because of this, there are a total of 4 possible outcomes in your classic hypothesis test situation. The null hypothesis might be true. The null hypothesis might be false. So we have these 2 ideas with the null hypothesis. Like I mentioned above. But we make a decision to reject the null hypothesis. And if we reject the null hypothesis and the null hypothesis was false, well, we made the correct decision. On the other hand, if we do not reject the null hypothesis and the null hypothesis turned out to be true, then again, we made the correct decision. However, if we reject the null hypothesis and the null hypothesis actually turned out to be true, then we made an error. This is in fact what we'd call a type 1 error. And perhaps we did the other thing where we did not reject the null hypothesis, but the null hypothesis actually was false. Then we created a type 2 error, or we perpetrated a type 2 error. So one of the reasons we do this backwards, where we set up a null hypothesis, is because it's easy for us to figure out the probability that we made a type 1 error. And that probability actually is the value of alpha. Recall here, if we wanted to be 99% confident, so we had a level of significance of alpha equals 0.01 or 1%, then if we were to find, if we end up with our z-score over here in the critical region, this critical region, which I'm gonna make blue right now, this is the critical region in this, and if our z-score ends up being over here, someplace greater than 2.58, so if we end up with a z-value greater than 2.58, that means that we're inside the critical region, then we would reject the null hypothesis and conclude, in this case, that our pipe exceeds the 2,400 pounds per square inch strength. However, it's possible that we are wrong, and we have a 1% chance of being wrong. So what we're saying is we're 99% confident that we made the right decision by rejecting the null hypothesis there. Since our value of z ended up over here in this critical region, we reject the null hypothesis. But what could potentially have happened is this could just be a statistical anomaly. We could have just potentially just got really high values of strength out of our test specimens than is average for the strength of all the specimens in the warehouse. And in that case, we would be wrong. And since we rejected this null hypothesis, when actually it was true, this would be a type 1 error. So the area of the level of significance is the chance that this happens. and that's 1%. And that's why we do these hypothesis testing kind of in a backwards approach, because it's easy for us to calculate a type 1 error. Now, the type 2 error is a little more complicated, and we're not going to really go into figuring out how to calculate the probability of a type 2 error in this class. But we only concern ourselves with the type 1 error. So all this might sound a little complicated and possibly hard to understand at this point. And that's okay. That's not unusual if you feel that way. So let's run through this pipe example. Using a hypothesis test. So the first thing we're going to do is we're going to determine what our alternate hypothesis is and what our null hypothesis are. So H naught and H1. And of course, let me write the problem statement here again. So I shrunk down and pasted the problem statement from above here. So from the information we have, we see that our alternate hypothesis, what we want is we want to ensure that the mean strength is greater than 2400 psi. So our alternate hypothesis, then we're going to put equal to 2400. And it's implied, like I said, that it's less than or equals good. But we don't have to do every case less than 2400. In order to prove this is correct, we can just start at 2400 as the most conservative value. So mu equal to 2400 is a fine way to set up our null hypothesis. Okay, and then we want to be 99% sure, so we want to do this at a level of significance alpha equals 0.01. So put in parentheses here. We call this our level of significance. Okay. All right. So now, next step is let's calculate a test statistic. So for this, we're going to use z equals x bar minus mu over sigma minus square root of n. So I have to find these values. And I'll pull these values out of the word problem. Well, to start with, x bar is the sample mean we pulled here. X bar equals 2460 psi. Mu is the mu from our problem. It's 2400. N is our sample size, 15. And now we're at sigma. Well, sigma, we would need to know what the population standard deviation is. And it wasn't given in this problem. But if I were to give you this as a problem on an exam or something, I would give it to you. So I'm just going to throw one in here. I'm just going to say sigma equals 200. So it's the same as this sigma down here. But let's just say sigma equals 200. Okay, let me pick this up in the next video.